Welcome to this video where we explore computer vision. Have you ever wondered how a self-driving car recognizes pedestrians, cars, bicycles, and traffic lights? Or how a security camera can automatically detect and track people? To us, recognizing objects seems effortless, but for a computer, an image is simply a collection of pixels. So how does AI know what objects are in an image and exactly where they are? The answer is object detection. In this video, we'll explore the evolution of object detection from RCNN to YOLO. You'll learn the key ideas behind bounding boxes, IOU, non-maximum suppression, faster RCNN, mask RCNN, and YOLO. By the end of this video, you'll understand how modern object detection systems work and why they power technologies like self-driving cars, robotics, medical imaging, and smart surveillance. Let's dive in and see how object detection works.
A human can look at this image for less than a second and immediately recognize cars, people, bicycles, and traffic lights. But for a computer, this is simply a grid of pixel values. So how can a neural network determine not only what objects are present, but also where every object is located? And how did object detection models evolve from slow systems that examine thousands of regions separately to models such as YOLO that can process video in real time? That is what we are going to explore in this video. Let us begin by separating three closely related computer vision tasks. In image classification, the model assigns one label to the entire image. If we provide this image to a classifier, it might predict that the image contains a dog. But the model does not tell us where the dog is. In object localization, the model predicts both the class of the main object and a bounding box describing its position. Object detection extends this idea further. An object detector can identify multiple objects in the same image, assign a class to each one, and predict a separate bounding box for every detected instance. So image classification answers only one question: what is in the image? While object detection answers two: what is in the image, and where is it? The position of an object is usually represented with a bounding box. A bounding box can be encoded using the coordinates of two corners, or by its center point, width, and height. Along with each box, the detector normally produces a class prediction and a confidence score. For example, this output means that the model believes there is a car inside this region with a confidence of 91%. But predicting a box is not enough. We also need a way to measure how closely the predicted box matches the true location of the object. For that, object detection systems commonly use intersection over union. Intersection over union, usually abbreviated as IOU, measures the overlap between two bounding boxes. One box is typically the ground truth box supplied in the training data, and the other is the box predicted by the model. To compute IOU, we divide the area shared by the two boxes, the intersection, by the total area covered by either box, the union. If the boxes do not overlap, the IOU is 0. If the predicted box perfectly matches the ground truth, the IOU is 1. Therefore, a higher IOU generally indicates a more accurate localization. During evaluation, a prediction may be treated as a correct detection only if its IOU exceeds a selected threshold. For example, with a threshold of 0.5, this box would count as a match, while this one would not. There's another problem. An object detector rarely produces only one candidate box for each object. It may generate many boxes at slightly different positions and scales, all describing the same person. We do not want to display every one of them. We need to preserve the best prediction and suppress the duplicates. This post-processing procedure is called non-maximum suppression, or NMS. It begins by selecting the bounding box with the highest confidence score. Then in step 2, we create an empty list to store final boxes. In step 3, we pick the box with the highest confidence score and call it B_max. In step 4, we compare the IOU of B_max with every other boxes. Any box with an IOU greater than the threshold is considered to overlap too strongly with the selected box. It is therefore assumed to represent the same object and is suppressed. The algorithm then selects the highest scoring box that remains and repeats the process. As you can see in this iteration, the yellow box has the highest confidence score and will be added to the keep list. Then its IOU with the remaining boxes will be calculated, and as in this example, both red and purple boxes, has IOU greater than threshold, will be considered as the same object and are suppressed. And finally, here's our final result. Here, the IOU threshold is very important. If it is too low, the algorithm may accidentally remove boxes belonging to nearby objects. If it is too high, duplicate detections may remain. NMS is therefore not part of recognizing the object itself. It is a post-processing step used to clean up the detector's output. The first stage of RCNN implementation uses an algorithm called selective search to identify regions of interest by keying on similarities in color, texture, shape, and size. This figure shows the first 500 bounding boxes generated when OpenCV. Implementation of selective search examines an image. These regions are known as region proposals. The original RCNI could generate roughly 2,000 proposals for a single image. Each proposed region is cropped, resized to a fixed input size, and passed independently through a convolutional neural network. The CNN extracts a feature vector from the region. Those features are then used by separate classifiers to determine the object category, while a bounding box regressor refines the position of the box. RCNN achieved strong detection accuracy for its time, but it had a major weakness. Thousands of overlapping regions had to pass through the CNN separately. This meant that the network repeatedly processed the same image pixels, making both training and inference extremely slow. Let's first understand why the original RCNN was so slow. Suppose this is our input image. It contains a car, a bicycle, and a dog. The first step is to generate thousands of region proposals that might contain objects. Typically, around 2,000 candidate regions are produced at. Now here's the problem. Each one of these regions is cropped from the original image and passed through the CNN independently. That means the CNN has to process almost the same image again and again and again. Many of these regions overlap heavily. As a result, the most computationally expensive part of the pipeline is repeated nearly 2,000 times for a single image. This makes RCNN very slow. Now let's see how fast RCNN solves this problem. Instead of sending every region through the CNN separately, fast RCNN processes the entire image only once. The CNN produces a feature map, which is simply a compact and information-rich representation of the whole image. Think of the feature map as a smart summary. Instead of storing raw pixel values, it stores meaningful visual features such as edges, textures, corners, wheels, windows, or fur. Now, instead of cropping the original image, every region proposal is projected onto this feature map. Each region is then converted into a fixed-size representation using ROI pooling. Finally, those features are passed to the classifier and the bounding box regressor. The key advantage is that the expensive convolutional computation is performed only once. All region proposals simply reuse the same feature map. That is why fast RCNN is dramatically faster than the original RCNN. In 2016, a paper titled Faster RCNN further boosted performance by replacing selective search with a region proposal network called RPN. The RPN is a small neural network that operates directly on the shared feature map. As it moves across the feature map, it evaluates several reference boxes with different sizes and aspect ratios. These reference boxes are called anchors. For each anchor, the RPN predicts two things. First, an objectness score, and second, a set of coordinate adjustments that moves and resizes the anchor so that it better fits the potential object. The best proposals are then sent to the detection head, which predicts the final class labels and bounding boxes. The important idea is that both the proposal network and the detector use the same convolutional features. That is why faster RCNN is both faster and generally more effective than fast RCNN. Faster RCNN tells us what each object is and where its bounding box is located. But a rectangular box does not reveal the exact shape of the object. Mask RCNN extends faster to RCNN by adding a third prediction branch. In parallel with class prediction and bounding box regression, the model produces a pixel-level segmentation mask for each detected object. This task is called instance segmentation. The word instance is important. If an image contains 3 people, the model does not simply label all person pixels as one region. It produces a separate mask for each individual person. This makes Mask RCNN useful for applications such as background replacement, image editing, robotics, and medical image analysis. Mask RCNN also replaces ROI pooling with a more accurate operation called ROI align. ROI align avoids some of the small localization errors introduced by ROI pooling, making pixel-level segmentation much more precise. The idea behind ROI align is quite interesting and deserves its own dedicated video. So to keep this video focused on object detection, we'll leave the implementation details for another time. The RCNN family belongs to a broader category known as two-stage detectors. In the first stage, the model generates candidate object regions. In the second stage, it classifies those regions and refines their bounding boxes. In real-time applications such as autonomous driving and video analytics, speed is very important. This motivates a different approach. Rather than finding regions first and classifying them second, can one neural network predict everything directly in a single pass? This is the central idea behind YOLO. You only look once. YOLO reframes object detection as a single prediction problem, instead of generating region proposals and processing them through a separate detection stage. A single neural network predicts object locations and class probabilities directly from the complete image. The image is analyzed in one forward pass. That is, the source of YOLO's name and much of its speed. In the original YOLO formulation, the image is divided into a grid. One of the most important ideas in YOLO is that each object is assigned only one grid cell. Specifically, the grid cell that contains the center point of the object is responsible for detecting that object. For example, as you can see in this image, only the yellow and red grid cells are responsible for detecting the pedestrian and the car, because the centers of those objects fall inside these cells. Even though parts of an object may extend into neighboring grid cells, those cells are not responsible for predicting that object. Only the cell containing the object's center predicts its location and class. Now you might be wondering how this actually works. A common misconception is that each grid cell is processed independently by the CNN. That's not the case. The entire image is passed through the convolutional neural network as a whole. The CNN then produces a feature map, and each location on this feature map corresponds to one grid cell in the original image. After the image passes through the CNN, the network produces a feature map like the one shown here. For each grid cell, the network predicts a vector containing x and y, the coordinates of the bounding box center, w and h, the width and height of the bounding box, a confidence score, which indicates how confident the model is that an object exists in that box, and finally, the class probabilities. If each grid cell predicts B bounding boxes, and there are C object classes, then the output tensor has the following dimensions. This means that for every grid cell, the network outputs 5 values for each predicted bounding box, x, y, w, h plus c, which is confidence class probabilities. Another important parameter is b, which is a hyperameter of the model. b specifies how many bounding boxes each grid cell predicts. For example, if b2, then every grid cell predicts 2 different bounding boxes. If b equals 3, each grid cell predicts 3 bounding boxes, and so on. The fifth value is the confidence score. But what exactly does this confidence represent? In the first version of YOLO, the confidence score is calculated as the probability that an object exists inside the predicted bounding box, multiplied by the intersection over union, or IOU, between the predicted box and the ground truth box. This means the confidence score is high only when 2 conditions are met. First, the model is confident that an object is actually present. Second, the predicted bounding box closely matches the ground truth box. Later, this confidence score is used to filter out weak predictions before applying non-maximum suppression. Finally, the network predicts the class probabilities. Suppose our dataset contains 20 object categories, such as person, car, bicycle, dog, and so on. In that case, C equals 20. This means that for each responsible grid cell, the network outputs 20 numbers, where each number represents the probability that the detected object belongs to one of those classes. As an example, let's look at the output vector for this grid cell. Since the center of the pedestrian falls inside this cell is responsible for detecting the object. The first 4 values, x, y, w, and h, define the location and size of the predicted bounding box. The next value is the confidence score, which is very high in this example. indicating that the network is highly confident about this prediction. Finally, the remaining values represent the class probabilities. Here, the highest probability corresponds to the person class, so the network classifies this object as a person. Every grid cell in the image produces a similar output vector, and together these vectors form the final output of the YOLO network.
During training, the network learns better values. Predictions become increasingly accurate. We usually end up with multiple overlapping boxes. NMS removes the redundant boxes, giving us the final output.
Here we should add something. A YOLO detector may still produce several candidate boxes for the same object. In many traditional YOLO pipelines, confidence filtering and non-maximum suppression are applied after the network prediction to remove weak and duplicate boxes. So although YOLO avoids the region proposal pipeline used by RCNNs, the basic duplicate box problem still exists. The difference can now be summarized simply. Faster RCNN first proposes regions, and then analyzes those regions in a second stage. YOLO predicts boxes and classes directly from the image in one detection pipeline. This generally gives YOLO a major speed advantage, making it particularly attractive for real-time video. But this should not be reduced to the statement that one model is always better than the other. The correct choice depends on the data set, required accuracy, object sizes, hardware, and latency constraints. In practice, modern implementations from both families have improved considerably.
Thank you so much for watching and making it all the way to the end of this video. Today, we explored how object detection evolved from the original RCNN to fast RCNN, faster RCNN, mask RCNN, and finally, YOLO. We also learned the key ideas behind bounding boxes, intersection over union, non-maximum suppression, feature maps, region proposal networks, and why YOLO became one of the fastest object detection algorithms ever developed. I hope this video helped you build an intuitive understanding of how modern object detection systems really work. If you found this video helpful, please give it a thumbs up and subscribe to the channel. It really helps support the channel and motivates me to create more in-depth AI and machine learning content. Thanks again for watching, and I'll see you in the next video.